Have you ever wondered why hot objects glow? It's a question that has fascinated scientists and curious minds alike for centuries. A piece of metal, heated to extreme temperatures, emits a bright, fiery light. This glowing effect is not just limited to metal. It can be observed in many materials when they are heated sufficiently. This fascinating phenomenon is called blackbody radiation. It's a fundamental concept in the field of physics that helps us understand how objects emit light and heat. Imagine a whimsical world of claymation where a tiny glowing ball of clay represents a blackbody. This blackbody is a perfect emitter and absorber of radiation. A blackbody is an idealized object that absorbs all electromagnetic radiation incident upon it. No matter the wavelength or frequency, it takes in all the energy. It's like a perfect absorber of light and heat. This means that no radiation is reflected or transmitted, only absorbed. When a blackbody absorbs energy, it heats up and emits its own radiation. This emitted radiation is what we observe as the glowing light. This emitted radiation has a characteristic spectrum that depends only on the object's temperature. The hotter the object, the more intense and varied the spectrum of colors it emits. Picture our claymation blackbody glowing with the spectrum of colors, shifting from red to orange to yellow as the temperature rises. This shift in color is a direct result of the changes in temperature. Blackbody radiation was a puzzle for physicists in the late 19th century. They observed the spectrum of light emitted by heated objects but couldn't explain it using classical physics. Classical physics, the prevailing theory at the time, couldn't explain the observed spectrum of blackbody radiation. Enter the ultraviolet catastrophe. This was a major problem that led to the development of quantum mechanics, a revolutionary new way of understanding the physical world. It was Max Planck who first proposed a solution to this problem. He introduced the idea that energy is quantized, meaning it can only be emitted or absorbed in discrete amounts called quanta. This groundbreaking concept laid the foundation for modern quantum theory. Planck's formula accurately described the observed spectrum of blackbody radiation, resolving the ultraviolet catastrophe and opening the door to a new era in physics. This discovery not only explained blackbody radiation, but also paved the way for many other advancements in science and technology. Today, the principles of blackbody radiation are applied in various fields, from understanding the cosmic microwave background radiation to developing advanced thermal imaging technology. The study of blackbody radiation continues to be a vital part of scientific research and innovation. So the next time you see a glowing object, remember the fascinating world of blackbody radiation and the incredible journey of discovery that has helped us understand the nature of light and heat. Classical physics predicted that a blackbody should emit an infinite amount of energy at high frequencies, such as ultraviolet light. This prediction was based on the Ryleigh-Jeans law, which worked well at low frequencies but completely fell apart as the frequency increased. The higher the frequency, the more energy it predicted, leading to an absurd conclusion: infinite energy at ultraviolet frequencies. Imagine our claymation blackbody exploding with a blinding flash of ultraviolet radiation. This dramatic visualization helps us understand the severity of the problem. If classical physics were correct, every object would be emitting an infinite amount of energy right now, which is clearly not the case. This obviously didn't happen in reality. The real world doesn't behave this way, and scientists were left scratching their heads trying to figure out where they went wrong. The Ryleigh-Jeans law, a classical physics formula, attempted to describe the spectrum of blackbody radiation. It was a valiant effort, but it had a critical flaw. However, it failed miserably at high frequencies, leading to what became known as the ultraviolet catastrophe. This term was coined to describe the disastrous prediction of infinite energy. The law's prediction of infinite energy was a major problem, a catastrophe for classical physics. It was a clear indication that the existing theories were incomplete and couldn't fully explain the phenomena observed. The ultraviolet catastrophe demonstrated that classical physics was incomplete. Scientists were puzzled and knew they needed a new approach to solve this mystery. It couldn't explain the behavior of light and matter at the atomic level. The interactions at these tiny scales were far more complex than classical physics could handle. A new theory was needed, one that could account for the quantization of energy. This realization paved the way for the development of quantum mechanics, a revolutionary framework that would change our understanding of the universe forever. In 1900, Max Planck, a German physicist, proposed a revolutionary solution to the ultraviolet catastrophe. He suggested that energy was not continuous, as classical physics assumed, but rather came in discrete packets called quanta. Imagine our Claymation blackbody emitting energy in tiny bursts, like a miniature fireworks display. Planck's quantum hypothesis was a radical departure from classical physics. It implied that energy was not infinitely divisible but rather had a fundamental unit, now known as Planck's constant. Planck himself was hesitant about the implications of his theory, but it perfectly explained the observed spectrum of blackbody radiation. Planck's quantum hypothesis marked the birth of quantum mechanics, a revolutionary theory that governs the behavior of matter and energy at the atomic and subatomic levels. Quantum mechanics has profoundly changed our understanding of the universe and has led to countless technological advancements. The idea that energy is quantized has had a profound impact on our understanding of the universe. It has led to the development of lasers, transistors, and countless other technologies that rely on the quantum nature of light and matter. Section 5. The legacy of quantum mechanics, from lasers to quantum computers. Quantum mechanics has revolutionized our understanding of the universe, from the smallest particles to the largest structures in the cosmos. It has given rise to groundbreaking technologies such as lasers, transistors, and nuclear energy. Lasers, for example, rely on the quantum phenomenon of stimulated emission, where photons interact with atoms to release identical photons, creating a highly focused beam of light. Transistors, the building blocks of modern electronics, rely on the quantum behavior of electrons in semiconductors. Section 6. Quantum mechanics in everyday life. From smartphones to medical imaging. Quantum mechanics is not just a theory confined to laboratories and research institutions. It plays a crucial role in our everyday lives, powering the technologies we rely on. Smartphones, computers, and medical imaging devices all rely on the principles of quantum mechanics. For example, the touchscreens on our smartphones use transistors, which rely on the quantum behavior of electrons. Medical imaging techniques such as MRI or magnetic resonance imaging rely on the quantum properties of atomic nuclei. Section 7. The future of quantum mechanics. Exploring the unknowns. Quantum mechanics continues to be an active area of research with many mysteries yet to be unraveled. Scientists are exploring the potential of quantum computing, which could revolutionize fields such as medicine, material science, and artificial intelligence. Quantum computers exploit the strange and counterintuitive properties of quantum mechanics, such as superposition and entanglement, to perform calculations that are impossible for classical computers. These powerful machines have the potential to solve some of the world's most challenging problems. Section 8. Claymation, a creative lens on quantum concepts. Claymation, with its whimsical and tactile nature, provides a unique and engaging way to visualize complex scientific concepts like quantum mechanics. By using claymation to represent atoms, photons, and other quantum entities, we can make these abstract ideas more accessible and relatable to a wider audience. Imagine a claymation animation showing the wave-particle duality of light, with a photon transforming from a tiny ball of clay into a rippling wave. Such visualizations can help to demystify quantum mechanics and inspire curiosity about the quantum world. Section 9. Conclusion. The enduring allure of the quantum world. The ultraviolet catastrophe was a pivotal moment in the history of physics. It marked the failure of classical physics to explain the behavior of blackbody radiation, leading to the development of quantum theory. This crisis in physics opened the door to a new way of thinking about the fundamental nature of reality. It led to the birth of quantum mechanics, a revolutionary theory that has transformed our understanding of the universe and our place in it. Quantum mechanics introduced concepts that were once thought impossible, such as wave-particle duality and quantum entanglement. These ideas challenged our classical intuitions and reshaped the landscape of modern physics. From the smallest particles to the largest structures in the cosmos, quantum mechanics governs the behavior of matter and energy. It provides the framework for understanding phenomena at the atomic and subatomic levels, as well as the dynamics of stars and galaxies. The principles of quantum mechanics are essential for explaining the intricate dance of particles and forces that make up our universe. As we continue to explore the strange and wonderful world of quantum mechanics, we can be sure of one thing: the quantum world will continue to surprise and amaze us. revealing the hidden workings of the universe and inspiring new technologies that will shape our future. Quantum mechanics has already given rise to innovations such as quantum computing and quantum cryptography, which promise to revolutionize fields ranging from information technology to secure communications. The journey into the quantum realm is far from over, and each discovery brings us closer to unlocking the mysteries of the universe.